Should I just get started, or? Okay. Hello, everyone. Thank you for coming. So I'm Sunjay Cauligi from UC San Diego. I'm here to talk about some work that I, along with a whole host of collaborators, have been working on in the domain of constant-time programming for cryptography, and specifically a DSL we've created called FaCT. So what is constant-time programming? Constant-time programming is meant to help with timing side channels. So when you're doing crypto, so let's say you have a secret key, you have some plain text, you run it through your crypto libraries, and you get some encrypted text out the other end. And what you want to make sure that does not happen is your secret keys or your unencrypted plain text leaks, because that is very bad and kind of defeats the whole point of doing the crypto in the first place. The problem is, if there are any timing differences in your crypto implementation based on the values of the secret key or based on the values of the plain text, an attacker with a stopwatch essentially can time your crypto routines and use that timing variation to learn something about your secret keys or plain text, and they get leaked via timing. That's really bad. So I can go over a more concrete example. So we're going to implement a function that checks for PKCS7 style padding, where each padding byte holds the length of the padding. So in this example, we have a buffer. Apologies for those in the back. I know it's really hard to see the bottom of the screen. But we have a buffer, and say we have 5 bytes of padding, then the last 5 bytes of this buffer all hold the value 5. And we're going to write a function that replaces the padding with null bytes, as well as checks that the padding is valid, and then returns the padding length or some error code. And what we have to be careful about is that this buffer is considered secret. So the entire contents of the buffer are secret, including the padding length itself. So we want to make sure that we don't leak the length of the padding. So a very naive example that I can walk us through. So we're going to check the very last byte of the buffer to get the amount of padding we expect to be there. So in this case, we get the value 5. Then we're going to loop over that many times each value, check that it is the proper value in the padding, and zero it out, and then return the amount of padding at the end. So let's say, for the sake of argument, that each time through the loop takes roughly 10 microseconds. So overall, this routine took 50 microseconds on this buffer. But what happens if we have invalid padding? Say this middle byte is 7 instead of 5. Then when we loop through, we're going to trigger this error condition partway through our processing. And so after 20 microseconds, we immediately fail out. And this is bad because this is a timing difference, 20 microseconds versus 50 microseconds. So the attacker can learn something about this data, namely that there was invalid padding somewhere along in here. And this is known as a padding oracle. It seems like it should be inconsequential, but padding oracle attacks are actually, they're the real-world attacks against OpenSSL and other cryptographic libraries based off exactly this type of padding oracle. So this is something we want to avoid. And the way people do this, one of the most common ways people do this is constant-time programming. What this essentially is you have some recipe of sorts where you say, I have this problem, I want to get rid of it, how do I do that? So in this case, our problem is we're returning early in our function. So our recipe is, instead of returning right away, we're going to create this new variable that's whether or not we're OK. And instead of returning immediately, we'll just set that we're not OK. And then at the end of the function, we return the proper value. So now we process all 5 bytes, even though we would have errored out initially. But instead of stopping immediately, we keep going. And then just at the end of it, we say, OK, it was actually bad the whole time. So that's cool. But this was for if we have 5 bytes of padding. If we have 3 bytes of padding instead, or some other amount of padding, then we're only going to iterate over those bytes of padding. So now we have 30 microseconds instead of 50 microseconds. So again, we're leaking the amount of padding that we have, and that's bad. And the reason is because we're looping over this secret value. So the padding length is secret, but we're performing our loop that secret number of times. So how do we get rid of that? Well, we're going to use another recipe. instead of looping over just the secret amount of information, we're going to figure out the maximum value of padding. So since the padding value has to fit in a single byte, we know we have a maximum of 255 bytes of padding. So what we're going to do is we're going to always loop over the final 255 bytes of the buffer. But we'll only process the bits, the bytes that are the padding we care about. So now, even though there's only 3 actual bytes of padding, we're going to pretend as if there's a whole bunch more padding, just so that there's no timing difference anymore. So that's cool. But if we take a look at our code, when we're operating on the padding bytes, we're executing all of that code inside the loop. And when we're looping over the non-padding bytes, we're only executing over that much code. So it's not really 10 microseconds for every iteration, it's maybe more like 10 versus 9. And so now we have another timing difference between these two sections, and we have another padding oracle. And so what we're going to do is we're just going to get rid of all branching entirely. So there's no more branch conditions. We're going to make it straight line code inside of this for loop. And this is where things start getting really ugly. So don't worry about trying to actually read this code. It's really gross. But this is the kind of code that you'll see if you open up the OpenSSL source code. They're using all of these macros. They're doing all of these bit hacks to get at this way of avoiding using branches so that they can execute everything in constant time. And so we're doing a bunch of extra computation because we have to kind of necessarily. So maybe we're up to 12 microseconds. But now we are actually constant time for all of these things. So the attacker will not be able to learn anything about any secret values based on the timing of this program. But the end result is pretty nasty. And so this was a toy example, but this kind of stuff shows up in the real world. So I keep harping on OpenSSL. So the original OpenSSL, there was a padding oracle attack. And this is kind of just a screenshot of the diff from GitHub that fixed this padding oracle attack. In the code post-patch, there was another timing attack because there were still some subtle timing differences that they hadn't fixed. And this is what led to the Lucky 13 timing attack. And even then, there were still further timing variations that people hadn't found, that they found over the years. And so after this patch, there were no more timing differences in this code path through OpenSSL, which seems like it should be great. But there was still one more bug that was found 3 years later. And it wasn't a timing vulnerability. It was just a straight up missing check in the code. So it's literally one line to fix it. But this went undiscovered for 3 years because all of this code in the surrounding area is really nasty to work with, and it's really difficult to tell that this actually was a problem. So constant time code is really hard to work with. It's hard to reason about. You have to manually keep track what is public, what is secret. You're folding your control flow into data. And it just makes everything really hard to maintain. And so if you were at Jesse's talk just before this, this is exactly the kind of pain that we would like to defeat with DSLs. So what we're going to do is we're going to create a DSL, domain-specific language, that will help us in all of these areas. So keep track of what is public, what is secret, help us write cleaner code, help us reason about things a lot nicer. So enter FaCT. If you have sensitive cryptographic functions that you want to write, you write them in the FaCT language in a FaCT file, run it through our compiler, which will generate a header file and an object file. And these are just normal. It's a C header, it's a C object file, so you can link these right in with the rest of your code base and get your final binary. So we don't expect you to rewrite your entire code base in FaCT, just the functions that are timing sensitive, essentially. So what does FaCT look like? Well, it looks pretty much like C. You may notice off the bat we have explicit labels. So if anything is secret, the return value in this case is secret, the inputs are secret. We have a secret temp variable. We also have some things like explicit mutability. Unless otherwise stated, something is immutable. But for the most part, the rest of it looks fairly C-like. And you'll notice we're actually using conditional statements, and we're returning early inside of the function. So this is an implementation of the example from the beginning of the slide deck. And even with this, I'm claiming that this is, in fact, constant time code. And it does exactly the same thing as our final result at the end of all of that, where it was super ugly. But I would argue this looks much nicer because we can reason about this in terms of, well, if I'm in this section, then do this, which is not something that was easily parsable in that C code. So at a really high level, all FaCT is doing is taking all of those recipes that I talked about and applying them automatically. And so we can take a look at what some of these recipes are. So the biggest thing is we remove branches. So all of this static control flow, if you have secret branching, we can transform each of those assignment statements into these sort of constant time selections. So if S and S2 are both true, then X will get assigned the value 42, otherwise it will stay the same. Same for the next case, same for the next case. So like if S is true, then Y will get assigned X plus 2, otherwise it will stay the same. And so CT select is not an actual function we generate. It would be implemented in terms of the same bit hacks that OpenSSL uses, or on x86, 64 systems, there is the conditional move instruction, which is actually, it does essentially the same thing, but it's a lot faster. So we can just directly use that and get some performance gains out of it. So similarly, in the case we have a secret branch with an early return inside, we can transform that into keeping track of a temp variable that's just the return value. And so each time, instead of returning, we just assign into a return value and then set whether or not this function has returned yet. So by the time we get to this second statement, we only set the return value if we have not already returned yet. So we keep the same semantics of if S was true, we return 42, otherwise we return 17. And we can do the same thing with, so if we have, in this case, a function that mutates its parameters. So if it has an output parameter. So in this case, this function assigns 42 to X. And we want to have the semantics where if S is true, then when we call this function, X should be updated to 42. But if S is false, then we don't want that to happen. And so what we can do is we can instrument the function to take an additional parameter, which is the caller state. And we pass that down into the function. So we still capture the same semantics of if S is true, then X will be updated, otherwise it won't. And it all happens in constant time. And kind of the underpinning of all of these transformations is our label model. So we have just a very simple secret versus public. We have the standard flow control of you cannot assign secret data into a public variable. And we also use these labels to track control flow. And we only need to perform transformations when we're in secret control flow. So if we're inside a secret branch, then we apply transformations to everything inside the secret branch. If we have a secret return, then all the code that comes after that secret return will need to be transformed. But otherwise, we don't need to transform the code. And we also use labels to prevent expressions that don't have a simple, efficient transformation. So for example, loop bounds. If you're trying to write code that is bounded by some secret value, we don't have an easy way of transforming that because we don't know what the proper transformation would be. So the compiler would just flag this as an invalid program and force the developer to change the loop bound to some public value. And then inside the loop, they can write a conditional statement saying, if we're actually in this secret bound, then do whatever operation. And then we can apply the same transformations that I showed you earlier to capture the same semantics. Similarly, if you try to index memory based on a secret value, this can actually lead to cache timing attacks. Because if your cache state is determined by secret values, then an attacker can do cache timing measurements to figure out what your accesses were. So in this case, we would flag this as an invalid program, and the developer, one way they could get around this if they really need to do a secret access is to bound their memory access by some public bounds. And so all the attacker would see is a publicly determined sequence of memory accesses. And then inside this loop, the developer can say, if we actually are at this secret value, then retrieve the value. And we would apply the same transformations as before, and this would all happen in constant time. And it's completely publicly determined. So this can also help with other subtle cases. So for example, on x86 systems, again, integer division, the amount of time that integer division takes actually can depend on the values of the operands. And so if you have a secret value as one of the operands, an attacker might be able to determine the value of that operand through the division. So again, we force these to be public. If you really need some sort of secret division, you can call some maybe more heavyweight function that performs the equivalent of division, but we prevent direct division with secrets, and modulo and other operations that would be variable time. Recursion is also difficult to reason about, because recursion is essentially just looping. And so you need to be able to determine that your recursion bounds are, in fact, public. It turns out most cryptographic code doesn't use recursion. I actually haven't seen any real-world crypto that uses recursion. So we just disallow recursion entirely. It's just the simplest thing, and it doesn't actually end up having much of an effect on the kind of code that we're targeting. So that being the case, transformations can be still a bit tricky. So for example, in this case, say we have some secret check that we have some passed-in mode that says, okay, this buffer is 32 bytes long. And so we check that, okay, if our buffer is in fact 32 bytes long, then we can do something at the end of the buffer, and it's fine. But if our buffer was not 32 bytes long, then we don't want to access index 31 because that would be an out-of-bounds memory access. Normally this would be fine, because if we fail that check, we just jump over this execution. The problem is, if this is a secret condition, then FaCT is going to transform this to straight line code, and we're always going to do this memory access. And this is an issue because secret if statements always perform both branches. They're just the nature of constant time programming. We remove all the branches and always execute all of the instructions in both branches. And what this means is we're going to end up doing this potentially out of bounds memory access, whether we should have or not. And so once again, the solution is to disallow this kind of program. And so we're going to do this by ensuring that FaCT is completely memory safe and has no undefined behavior, even with all of these secret if semantics. And so the FaCT compiler will actually generate constraints. So every memory access, it'll generate a constraint saying, is this actually an inbounds access? For undefined behavior such as division by 0, it'll make sure divisions don't have a 0 divisor. Bit shifts, it will make sure are within the bit width of whatever is being shifted. All of those kinds of things. And it's aware of these secret if semantics. So in this case, it wouldn't actually, it would be aware that this access is going to happen regardless of that condition. And it would flag this saying, this is potentially an out-of-bounds array access. You need to check this some other way. And so this is included as part of the compiler. So it will prevent programs that are not memory safe or have undefined behavior. Kind of along a similar vein, we check that we're generating constant time code not by verifying the compiler itself, but by running our generated code through an external verification tool. So in our case, we're using ctverif. And so every compilation, we just take our output code and run it through ctverif, and it'll say, yes, this is constant time, or no, it's not. And what this allows us to do, it's twofold. So one, we don't have to deal with verifying our compiler as we're developing it. And two, we can use, so we use LLVM. We can use the LLVM infrastructure to run all of the optimizations and without having to worry about whether or not it's going to break our constant time guarantees, because post-optimization, we run it through an external verifier, and it'll check whether we're still constant time. So I've been telling you how great FaCT is, but how good is it in actual practice? So for our case studies, we ported code from a variety of different cryptographic libraries. So we have libsodium crypto secret box, which is authenticated encryption. We did the decryption path from the OpenSSL TLS mode. So that's the same decryption path that I showed you the examples from that had all of the timing attacks in OpenSSL. And we also ported Montgomery multiplication from Mbed TLS and a Curve 25519 implementation. So looking at the performance numbers, this is for the OpenSSL code. The purple line at the bottom is C. So the C implementation in OpenSSL is still the best. The various FaCT ports, so we did a couple different variations where we did a direct port of the C code. We took the direct port and kind of untransformed some of the bit hacks into conditional statements in FaCT. And then the very top line, the yellow line, is kind of almost a complete rewrite, just purely in FaCT. So each one of those variations adds some amount of overhead, but in the long run, when we get to larger chunk sizes, it ends up the overhead drops to like maybe 5 to 15%. So we're still doing pretty well. And in the case of libsodium, we actually end up beating the C implementation. So on the left is encryption, on the right is decryption. The light blue is the C reference implementation from libsodium. And the dark blue is our FaCT ported implementation. And so we're just beating out the C ref implementation. The green bars are, so the light green is the C implementation in libsodium, but using assembly files to generate vectorized instructions. So taking advantage of the Intel SIMD vector instructions for faster processing. And the dark green is the FaCT implementation again, but with our compiler tweaked to emit those same vectorized implementations. And this is super cool because in C you have to resort to using either macros or inline assembly to get at these vectorized instructions. And in fact, we can expose these as part of our higher level language. And we're still beating out their implementation, which is really neat. We also conducted a usability study in my advisor's undergrad PL class. So we had them, we had a couple different sections where we had them understand code. So we gave them examples of constant time C, we gave them examples of FaCT, and they had to describe what the code was supposed to be doing. And we also had them write constant time code. We gave them an environment that had C plus a verification tool so that it would check that they're writing constant time code. And we gave them an environment where they could write FaCT code. And of course, we randomized the results, so different students got different languages in different orders. The main high-level takeaway is that, yeah, FaCT was actually pretty well received. It was easier for students to understand the code. Writing it, the main hang-up for students was just getting used to the syntax of a new language. But once they got beyond that, it was actually easier for them to write FaCT code than to write C code that was constant time. So that's pretty much what FaCT is at this point. Our future work, we want to be able to get better optimized transformations. So trying to get that last bit of performance so we can hopefully either match or beat the OpenSSL implementation, for example. We'd like to target other backends. So right now we're focusing pretty much just on x86 64. But the ARM platform has some use cases. There's some interesting things there where, so for example, on certain ARM platforms, 64-bit multiplication is not constant time. And so for each platform, we'd have different sets of intuition about what is useful instructions and what instructions we can use and what we can't. We're also looking to target CT-WASM. So this is another project that we're working on, taking WebAssembly and augmenting it with labels so that it can easily verify that the code is secure in terms of constant timedness. And so this would be great for crypto in the web or any other use cases that WebAssembly has, having fast verified cryptographic implementations. And of course, we would eventually like to verify the FaCT compiler itself so that we don't have to depend on an external verification tool. So kind of in summary, that was FaCT. It's a DSL for cryptographic programming. It takes care of doing all of this automatic transformation to constant time code. We've designed it to easily fit into an existing tool chain, so you can just grab it, run it, toss it into your C repo. We also have some pretty cool bindings for Python and Haskell, so you can write inline FaCT code and use it in Python and Haskell. And it's geared to be very usable and very fast. So thank you. That's all I have. I'll open it up for questions. Yes, I think they're coming with the microphone.
Hello, I'm Simon Peyton-Jones. A nice DSL. I've got sort of pair of questions. I had the idea that you were, as a result of writing your DSL, the code that you would generate would be more or less what you would have written by hand in C anyway with these CT things. So why is it any slower or any faster? And the sort of second half of the question is then, that code, once you feed it through LLVM, by definition, you have lots of dead code. So isn't there a real danger that a good LLVM optimizer might, undo all of the stuff that you've done?
Yes.
And indeed, that's what it's going to be trying very hard to do. So,
yes.
I mean, of course, that would apply equally to somebody who's writing the C with CT, blah, this and that.
Yes, those are both really good questions. So yes, our goal with FaCT is to generate essentially the equivalent of what you'd be writing by hand. The reason we are, in fact, the reason we're slower is that in a lot of cases, especially with, so the OpenSSL implementations, they do a lot of things where they're almost hand optimizing a lot of these parts and taking advantage of things that are specific to, for example, their AES CBC implementation. So we're applying just general case transformations right now, and so we don't necessarily know all of these other things that they can do that make things faster. So that's part of the reason why we're not as fast in that case. As to your other point of optimizations, yes, there is a danger of the optimizer getting in the way. So that's actually the reason why constant time code ends up looking so ugly. So if you look at C implementations, they'll end up doing, the reason you have to do all of these bit hacks and everything is to essentially trick the compiler into thinking that your code is not actually dead. And so
could you just tell the compiler? I mean, maybe we should talk to the people downstream, right?
Right. So you could, yes, you could start instrumenting the compiler itself to have like a constant time mode where it would do all of this, or some sort of security mode, and that would be super awesome. I don't know how difficult that would be for the compiler writers, though.
Maybe there'd be some kind of abstractions or some way in which you weren't really just saying generically run constant mode. You were saying, I'm going to explain to you, rather than tricking you, I'll explain to you, and then what would that abstraction or primitives? That would be an interesting question.
So that's actually part of what we're trying to do with CT-WASM, actually. So because CT-WASM is essentially WebAssembly with labels. And so it has the label information, and so it knows this is secret, don't mess with this. So.
I have a question to one of your questions. So what kind of dead code do you have? Because all the dead branches are actually merged into only one branch.
I didn't quite get the...
I was wondering what kind of dead code do you have, because all the dead branches in if statements, you're actually merging it into one path.
Right. So what? So it's not exactly dead code, but if you're not careful, a smart enough compiler can realize that regardless of the code, the kind of spaghetti code that you've written, you are actually writing branching statements and turn it back into branching code. And so it actually comes up in practice. LLVM has gotten really smart So if you, for example, if you try to use that, the bit hack manipulation, but the value that you're using is just a 0 or 1, it can do a value analysis and tell that this variable is only ever 0 or 1, and then turn it back into a branch. So you end up doing some other things to like mess with the compiler to prevent it from doing that.
Hi, Ed Barrett, King's College London. So I was wondering if the hardware had any means by which to kind of invalidate your guarantees. So does anything happen at the microcode level? For example, does it speculate on the condition of your conditional moves, or can it do anything like this?
So as far as we're aware, based on the papers that I've read, conditional move does not have any timing variations. That's based entirely on empirical measurements. The Intel spec, I believe, doesn't say anything at all about it. And one of my colleagues at UCSD has actually done a lot of work on floating point timing variation. And he has been very upset that it's very difficult to get Intel and some of the other architecture designers to say anything about how their instructions are implemented, because that's all very secret sauce stuff. And they spend a lot of time optimizing their instructions, which ends up meaning that there are timing variations because they introduce fast paths, and they're very loath to get rid of them because that means a performance hit. Yeah. So.
Yeah, sorry, you were mentioning you were working on this WebAssembly backend.
Yes.
And do you have anything in there to actually analyze the output WebAssembly? Is that what it is? To analyze it so that it's constant time?
Yes.
Like to actually analyze the output, not just the DSL for the input. So if I generate some WebAssembly,
Yes.
Do you guys have any plan for something that could analyze the outputted WebAssembly and say, well, this is constant time? Or,
Yes.
Yeah.
So CTWASM itself is actually an extension of the WebAssembly spec, so it includes labels as part of the type system. But we also have some tools that, given some unannotated WebAssembly, you annotate just the function parameters, and then it does its best to propagate those labels throughout and generate a labeled form of WebAssembly, which you can then validate. So.
I'm just curious, is there any danger that somebody inexperienced could maybe move too many variables into the public tag and expose timing attacks that way?
Yes, so using this system, you do require some domain knowledge of whatever you're implementing. So you need to be sure that you do know what actually is secret and what is public. So if you're determined enough, you can just say everything is public, and then it would leak it. So we're hoping that the developer does have some knowledge of what is secret and what is public, and if they make mistakes, then this helps them catch it.
Sorry, you only have time for one last question.
Okay. A lot. So you mentioned that your usability study, most of the users had trouble with the syntax.
Yes.
And as label checking systems, I mean, everyone has trouble with label checking systems. That's always where it falls down, is that the users can't do the labels. This is a really simple label checking system. Was it just the labels, or was there some other part of the syntax that was a problem? This is like as simple as you can get.
I think the main issue was that they're undergrad students. Some of them have experience with C, some of them didn't. So they were learning C at the same time. And then FaCT is like, it's similar to C, but then it's just different enough where you can start kind of messing up. And also we're much stricter in terms of types than C. So I think that version of the language that we used for the usability study doesn't have implicit casting from a larger integer size to a smaller integer size. That was things like that were throwing a lot of people off.
Okay, but the sort of as syntactic extensions, just the mute keyword and the labeling is the only thing that you added.
So it's actually it's much more constrained. So we don't have anything like pointers. There's no pointer manipulation.
Yeah, no, I know you
yeah.
deleted lots of stuff. I just wonder,
Yeah.
did you add anything else that tripped them up?
In terms of that user study, it was pretty much just the labels and mutability, I believe, and then like the minor like where the brackets go for array syntax and things like that.
Sure.
Yeah.
Okay, cool. Thank you.
We can do one more.
Okay.
Yeah, there's somebody up here. Is it?
Maybe it's something, well, thank you for your speech, and I wanted just to ask about one of transformation, about with return. So it seems like it's actually a question about side effects. So do this FaCT, do FaCT have side effects, do global variables and stuff?
So we don't have global variables, but we do allow side effects through memory. So you can, so like I showed in one of the examples, we have output parameters. So you can it's essentially reference passing, and you can modify arrays. You modify memory through references and arrays.
Yeah. So the question is, if you just write a code which returns early,
Yes.
it can trick you into thinking that if it's in a secret path, trick you into thinking that this actually will return, but it won't. So you can some functions downstream can get some side effects on your program, and that the program will actually work not as you expected.
So the transformations actually take care of that. So that's the reason why we have all this transformation framework, so we keep track of whether or not this function has returned. And so if you do some side effect like assigning into memory, one of the conditions that it checks is, has this function already returned? And if so, the memory update will just assign the same value back in. So it doesn't actually have.
Basically, all your side effects are controlled. Like
Yes.
you know about all of them, so it's not like C.
Yes.
Okay, thank you.
Yeah.
Okay, let's
All right.
thank the speaker
Thank
again.
you.